Okay, so I've had some good questions this morning about one of your assignment problems, and that made me realize that I forgot to mention something very important about impedances, complex impedances. A great thing about them, they add just like resistors. So we already know our rules for adding resistors in parallel and in series. Complex impedances are going to be just that. They're going to add in exactly the same way. So let's prove that real quick. So the claim is that if I have Z1 and Z2, they add in the same way as resistors. So if I have a series combination, I will get an equivalent addition of the impedances. And if I have a parallel combination, that's going to be equal to a parallel equivalent impedance that adds in the same way that resistors do in parallel. So let's prove that really quickly. So we have three things to prove. We have three cases of impedances. We have inductors, resistors, and capacitors. So starting with resistors, Z is equal to R. And the proof that resistors add like resistors needs no proof. We're done. QED. Okay. We're trying to prove that everything else adds like resistors. So including Z equals R is a moot point. Okay, so let's move on to inductors. And if we recall, the impedance for an inductor was equal to just J times omega times L. We had an increasing impedance with frequency, and here's the claim. And we're going to use this fact that if we just add two inductors, we like make a solenoid with double the length, we're effectively just adding the inductance, okay? So the claim is that if I just treat these as impedances, they should add up. And let's just prove that. So the equivalent inductance of this combined inductor is just J omega L1 plus L2 with some very simple factorization. That's J omega L1 plus J omega L2, which is equal to Z1 plus Z2. So in the case of inductors and resistors, the series combination of the impedances add just like we would have had with resistors. Okay, how about the parallel combinations? Let's have a quick look at that. So in this case, we had that the inductance added like resistors. And we could probably wave our hands a bit and say like, well, it's got to be the same as resistors then. But let's formally prove it. Let's formally prove it. So the new inductance of this device here is as follows. Okay, I'm just plugging in the equation for what the new inductance is. And let's actually try to unpack that a bit and try to get the proof that they're going to add in parallel like they do with resistors. I'm going to multiply top and bottom by J omega. Full disclosure, I haven't actually gone through this recently, so I'm kind of following my nose with this proof. We'll see how it leads. So we're going to get that. And already I can see that I'm going to get J omega over Z1 plus J omega over Z2. So I'm going to multiply top and bottom by Z1 by Z2 in the first case, and vice versa. Okay. Again, I'm kind of flying by the seat of my pants here. There might be a more elegant way to do this, but we're going to get there, I promise. We have the same denominator, so we can just flip it. So I get J omega Z1 Z2 after flipping that denominator times J omega Z1 plus Z2. These J omegas are going to cancel out. And this Z1, Z2 is exactly what we had for the case of parallel resistances. So indeed, it is the case also that I had for inductors that Z1 in parallel with Z2 is equal to a new Z. I'll put an inductor here, such that ZL inverse was equal to the inverse sum, or equivalently, ZL was equal to Z1, Z2 over Z1 plus Z2. So what do we have so far? We have that for resistors, the impedances add in the same way that they did with resistors. For inductors, we still have this parallel addition of inductors leads to the parallel rule like it would for resistors. Same with the series rule. We have one more case, and that's capacitors. And by the way, we could go the other way. We could start with this general rule for inductance and use it to prove the addition rules for resistors, capacitors, and inductors. That's kind of backwards to how we've presented it. So we have one more final thing to prove. We have to prove that even for capacitors, this holds. And this is probably the most dubious claim, that because capacitors, they add the opposite way, right? They don't add like resistors. But the claim is that the impedances of them do. So let's do that. So let's first look at two capacitors in series. So we know that this is equal to a capacitor whose capacitance adds in parallel like this. So what's the impedance of this, this one on the right? So the impedance of this is equal to negative j over omega c, my parallel combination. But this is equal to minus j over omega times 1 over c, which is equal to 1 over c1 plus 1 over c2. That's what this 1 over c term is actually giving us. Okay, so that is very straightforwardly equal to negative j over omega c1 plus negative j over omega c2, or z1 plus z2. Okay, I have a sneaking suspicion that I could have done the inductors this way, but So we're almost done. We have 6 things to prove. Resistors in parallel, resistors in series, capacitors in parallel, capacitors in series, inductors in parallel, inductors in series, that all those cases have the impedances just add as they do with resistors, namely that in series, Z1 is equal to Z1 plus Z2, and in parallel, you get this funny inverse adding. 1 over Z is equal to 1 over Z1 plus 1 over Z2. The last piece of the puzzle is that we have to do this for capacitors in parallel. And from before, we had that these just add in the normal way. So let's see how this one works. The impedance of this thing is equal to negative j over omega, and that is equal to j omega c, all inverse, right? Because 1 over j is negative j. So we have that c is equal to c1 plus c2, and this is equal to negative j over omega c1 inverse, right? Using that negative j is equal to 1 over j trick again, plus the other term, which is negative j over omega c2. And we've got to invert that whole thing there. And this is equal to z1 inverse plus z2 inverse, all inverse. Okay? So all we did was a brute force, case-by-case analysis, and showed that whatever you have, whether you have a resistor, a capacitor, or an inductor, if I have, whatever the case may be, if I have Z1 and Z2, that's equal to 1 over Z1 plus Z2. And if I have a parallel combination, I get an equivalent impedance, which just adds in that way that parallel resistors do. And that's it.